Okay, Laverne is flying from Kansas City to Milwaukee with a connection in Dallas. The probability her first flight leaves on time is 20%. If the flight is on time, the probability that her luggage will make the connecting flight is 93%. But if the first flight is delayed, the probability that the luggage will make it is only 15%. What is the probability her flight left on time given that her luggage in Dallas, given she had her luggage in Dallas for her connecting flight? Round to the nearest three decimals. Okay, so they're giving us some probabilities here. Let's see if we can identify them. The probability her first flight leaves on time. So the probability of on time is 20%. Probability her first flight leaves on time is only 20%. That sucks. Okay, if the flight is on time, the probability her luggage will make the connecting flight is 93%. So we're conditioning on it being on time. We're told that it is on time. If it is on time, then what is the probability? Then the probability of her luggage being there is 93%. So the probability of having her luggage, L, is equal to 0.93. So that's what they gave us there. The probability of her luggage being there given that the first flight was on time. So that's a conditional probability. It says if the flight is on time, the probability that her luggage will make the connecting flight is 93%. But if the first flight is delayed, the probability that the luggage will make it is only 15%. So that means the probability that the luggage makes it, given that the first flight was not on time, that's the complement of being on time, is equal to 15%. So that's 0.15. So that's all the information they gave us. And what are they asking us for? Let's see. What is the probability her flight left on time, given that her luggage is in Dallas? So that means what's the probability that the original flight left on time given that the luggage is there with her? So I notice that this is the inverted probability for a probability we already have. And that's the dead giveaway that I'm using Bayes' theorem here. So for Bayes' theorem, I'm looking at the probability of being on time given that the first flight being on time given that she has her luggage is equal to the probability of having the luggage and being on time, and that's going to be divided by the probability of having the luggage. Now if any of these are given, we're golden, but if they're not, we can rearrange them. All right, for instance, the probability of luggage and on time, the numerator of this thing, we could be written as the probability of luggage given on time times the probability of on time, because that's the definition of the probability of L and O. It's the conditional probability times the probability of 1. So it's the probability of O times the probability of L happening given O has already happened. And I have those pieces of information. I have the probability of O being 0.2 and the probability of L given O being 0.93. So I have the numerator. Now do I have the probability of L? Well, no, I don't have the probability of L, unfortunately. But I know that the probability of L can be found by summing up two joint probabilities. For instance, if I have the probability of L and O, I can add that to the probability of L and not O, because the total probability of L would be given there, because it's the probability of L given the first flight was on time, plus the probability of L given the first flight was not on time or delayed. And those are the only two situations. The flight is either on time or delayed. There's no third option. So that would give us the total probability. But if you notice, we already found the probability of L and O and called it the probability of O times the probability of L given O. And this is the exact same thing, so that first term in the denominator is the exact same as the numerator. So I still have the probability of being on time times the probability of her having her luggage given that the first flight was on time. Now this first term here is the exact same thing. The probability of being on time times the probability of her having her luggage given that the first flight was on time. Plus, then I have to look at what this one is. I can write that one in terms of conditional probabilities too. That one would also involve the probability of not being on time being multiplied by the probability of her having her luggage given that the first flight was not on time or delayed. So this is Bayes' theorem right here. That's Bayes' theorem. And I have everything I need from that theorem. So let's gather it all. So the probability of the first flight was on time is 0.2. So I get 0.2. And the probability of her having her luggage given that the first flight was on time was 0.93. So that's times 0.93. Remembering that that's the first term in the denominator, this is just 0.2 times 0.93. And I'm going to add to it the other one, which is the probability of being late. Do we have that? Oh, we don't have the probability of being late. We didn't, that wasn't given to us. But we do know the probability of being on time, and being late and being on time are complements of each other. So all I have to do is 1 minus that 0.2 to get the probability that this flight is not on time is 0.8. So that's an 80% chance that the flight doesn't leave on time. So this is 0.8 for the probability of the flight being delayed. And I'm multiplying that by the probability of her having her luggage given that her flight was delayed, which is 0.15. So I did have everything I needed except I had to find a complement. All right, then once you have all that, you are pretty much good. We just have to do all these calculations here. So let's see. That's going to be 0.2 times 0.93 is 0.186, and that means that this is also 0.186, and then 0.8 times 0.15 is 0.12, so this is 0.12. Then when you add those together, 0.12 plus 0.186, the result is 0.306. And then last, we just do that quotient. So 0.186 divided by 0.306 is equal to 0.6078. And this is the probability of the first flight being on time given that we know she has her luggage.